real. And for people online, if you can see a camera, I'm raising my hand here. We're in the corner. Neil's here. There's a few of us here in the room. We have a full room tonight of like, I don't know, 40, 50 people or something. And that's really nice for us. We're going to pass through the slides, let you guys know what we're up to today. Welcome to country. We begin today by acknowledging the traditional custodians of the land on which we gather and pay respects to the elders past, present, and emerging. We extend that respect to our regional and Torres Strait Islander people here today and those on lands where we have people calling in from today. In addition to that, I guess most of us would be aware of this already, but we have the IAH Indigenous Groundwater Declaration, which Haley pioneered with Sarah work and more people, I guess. Yeah.
It's actually on the column wall over there, if you'd like to read the articles of the declaration.
So yeah, you can learn more about it if you don't know about it yet. But you can just Google it, and it's really nice philosophy and a really nice effort coming together. We thank our sponsors today. We're having a list of sponsors for this financial year. At the moment, we have SDAT, WSP, and AGE, and we really thank them for sponsoring us. They allow these kind of things that we have today happen. And in addition to that, really big thanks to SLR, because, you know, in SLR's land today. And, so yeah, that's sponsoring us as well tonight. So yeah, thanks a lot. In addition to sponsorship, if anyone from any company has the capacity to sponsor us, we'll really appreciate it. We have different options for sponsorship. You can get in touch with anyone from the committee, with myself, or with Lucy reading. She's on top of the sponsorships as well, and it really helps us. We also, for memberships, for individual memberships, you can just Google the webpage on how to become a member of IAH and renew your membership. So memberships, as we have said before, run in calendar year, and sponsorships run in financial year. So sponsorships started just 3 months ago. However, I would like to highlight that to be able to come to these talks and to enjoy what we're doing today, anyone is welcome, not just members. And that goes especially to students, because we've heard in the street that sometimes the students can be a little bit shy of coming and join us and being here in the room because they think they're going to get charged. That's not. Please let everyone know that this kind of talks are open to anyone. One of the main things that we do here locally in the Queensland branch are the technical talks, and this is one of them. So we've covered different subjects in the past. It's a really nice way to get together, to chat with your peers, to know what's happening in the industry, to update what we know and to stay on top of the latest research that Neil's going to show us tonight. And yeah, it's a really nice thing that I guess we can take advantage of. By the way, sorry, before we move that, Neil is actually one of the technical representatives of the Queensland branch with Nick Colson, but it's not just them. They do a lot of the heavy lifting. But we have a committee of people. We all do what we can do because we're all busy. Most of us, or many of us, are consultants. We have busy lives, so we all try and help each other where we can, and it's a team effort, really. So anyone's welcome to come and help us, and something that we appreciate. On some news, we have the ASI lecture next month. So on Wednesday, 27th of November, and we have Matt Becker from California State University coming to chat with us and to give us a talk. So we actually have, this might be a really nice opportunity to decide because we get to choose between two topics. He gave us an option, so we can have a talk on fiber optic and how we use it for groundwater, or we can have a talk on how groundwater impacts the people and ecosystems of the South Pacific Islands. So people who are interested in fiber optic, raise your hands. Yeah.
Online, can you raise your hand as well?
That's three. All right, that's like 8 votes fully counted. And South Pacific Islands, can you please raise your hands? People have spoken. All right. All right. We'll let him know. Now, more news. The 52nd Congress of IAH. So probably Kelly's the best person to talk about it.
Yeah, sure. Kelly's got a mouthful. Hi, everyone. I'm Matt Currell. I haven't met everyone here, but a hydrogeologist working at Griffith Uni here in Brisbane. And myself and a few others here are involved in the organisation of the IAH Congress, the big international congress that happens every year somewhere around the world. Kelly's on the technical, on the main conference organising committee. I'm actually chairing the technical committee in charge of trying to pull together the best ever program for an IAH Congress out of 52. It's going to be held in Melbourne, Australia. We've already got together a really nice venue for the Congress. We've got 5 or 6 awesome field trips that are in advanced stages of organisation across many different types of hydrogeology interest areas. And the call for abstracts is going to be open very soon, within a week or two, November. There's a Congress website, and if you haven't taken a bit of a look or put in your email address to register your interest, please do so now. The Congress is also looking for sponsorship still. We've locked in some really great sponsors so far, but absolutely looking for more great sponsors. So if you work for a company or an organisation that wants to have some visibility and presence at a really big international hydrogeology event, hit us up and let us know. We'd to organise you with a booth or one of the other sponsorship packages. Everyone's mad keen on their interest area in hydrogeology here, I'm sure, and so you might have an idea for A, an abstract that you'd like to submit and talk about at the Congress, or B, maybe a session where you think there's a few people who might be able to get together and put forward a program of say 4 or 5 talks in one field that we can lock in as part of the program and make it a really star-studded and interesting cast of speakers for the day. Kelly, what have I missed?
I think you've covered it really well. Please share the word, speak to your colleagues, speak to your managers about what you'd like to present. Yeah, start getting the ball rolling with the planning, please.
Yeah, we can't wait. It's super exciting, and it's been an idea that was thrown around for a few years, and now it's finally actually happening. So yeah, we'll see you all there, and hopefully you help us spread the word and get a really good turnout.
Thanks a lot. All right. More quick news in case you missed this one. This one is fresh off the oven. We have a new groundwater sampling and analysis field guide. It was published 2 weeks ago, I think, if that interests you. Events for the rest of the year. So we have today's talk. Next month, we have the DASI lecture. In December, we have the Christmas party, which is getting organized at the moment. Claire Stevenson has been looking at all the logistics and more people, not just Claire. But it's all getting organized. If you want to get involved, it's all welcome. If you want to get in touch with us, look, I put the LinkedIn address at the top because that's the one where you can communicate with us straight away here in the ranch, in the state. All the other links that we have in there are more like connected with the general IIH people, which are OSCs and some of them, or it's about LinkedIn straight away. Or if you ask me, the best possible way to get in touch with us is here right now. Come say hi, and it's super nice. And then, well, live events. Let's hope all the audio and video works well. Again, any questions, just let us know on the channel, and we hope that works well. Most of you, or many of you, I guess, know Neil. Neil's groundwater model with a history here in Queensland and in Australia, and really good reputation. I personally admire a lot. He's been working independent for a while now, and he's been working on his PhD, and today he's here to present results of his research. So thanks for being here with us, Neil.
No problem. It's a very old photo. That look great here. Bring this up. Good.
Yeah, it's in there.
Yeah, thanks everyone for coming today. Yeah, I'm Neil Manewell. I'm in the closing phases of my PhD, which is should have been finished by now. Just writing up the thesis. My supervisor, John Doherty and Phil Hayes, who's here. So thanks to them. And I'm also an independent modeler and hydrogeologist. And today I thought I'd just present a bit of a whirlwind summary of my entire PhD over the last 4 years. So yeah, it's on understanding the meaning of estimated hydraulic properties from pumping tests and how to translate those properties into groundwater model parameters. So I thought the first thing I'll cover is the current state of how we would use an analytically derived TNS from a pumping test, how that's used to inform groundwater models. Then I'll cover the first paper, which talks about the meaning of those estimates, those Tice and Cooper-Jacob interpreted values of TNS. Then we'll cover the second paper, which is the new methodology to use these numerical fine-scale models to fit pumping tests and then upscale it, translate it to a model. And then finally, which might be the third paper or the sixth chapter of the thesis, how to extend that methodology to incorporate faults and dikes, and then a real-world example of that new methodology in practice. All right, let's go. So yeah, when I started off my career, I was a bit more of a hydrogeologist than a pure modeler like I am now. And you know, back in the day, that's a completely real, non-AI generated photo of me and Cole Hazel. He's teaching me how to interpret pump tests with tracing paper, and that's how I used to do it. And I learned a lot from him. It was fantastic working with him. But things have come a long way. And I guess, I mean, it has been a while since I've been interpreting pumping tests as a consultant. But my understanding, and I think a lot of hydrogeologists' understanding, is that when you undertake a pump test, you send a signal from the pumping test to the monitoring well, and you're expected to uncover surprises in the aquifer by looking at the signal, you know, from drawdown at the monitoring well. And I kind of thought that when I interpret TNS, what I'm averaging is TNS between the two wells, or at the monitoring wells or pumping wells. And what I've learned is that it's not quite right. And my experience was I would have problems fitting early time data in the pump tests. So these blue dots here, do you see that? There we go. Maybe I will use the laser pointer. There we go. That is not
Regular.
there.
Oh, yeah.
So I basically disregard early time data. Krusman and Derrida even recommend disregarding some of this early data, accommodating for heterogeneity in the aquifer, because these analytical solutions, they assume isotropic flow and aquifer parameters. They don't work too well when there is, heterogeneity in the system. And they even say that it's even recommended when that drawdown propagates across the aquifer, when you reach the pseudo steady drawdown, that's when you can approximate TICE and use Cooper-Jacob approximation, and what you end up with is this bulk average of TNS, and you quite successfully fit data just like in this example. So you fit it, you'll get moderate variability in TNS across those tests, even if there is a lot of assumed heterogeneity in the system. And then you'll populate a table with TNS, and that's kind of the range of TNS in the aquifer. But problematically, you kind of know that aquifer has more localized variability than that. And so what I used to do as a modeler, I used to get these estimates of TNS, put them in a table, or get them in as a table, and I'd say, well, actually, that aquifer is more like, it can be 1,000 meters squared a day, and the lower bound could be 0.01 meters squared a day. I'm not really going to use that data. I kind of disregard that data, and that data is expensive. It costs quite a lot to perform and interpret these pump tests. And then I might have done, back in a long time ago, performed a cardinal sin of saying, well, that aquifer is one parameter. So I'm going to say it is 40 meters squared a day, and I'm just going to allow PES to just change that one parameter. And in doing so, I'm kind of completely disregarding those pumping test estimates. They may as well not even be there. But conversely, I might put pilot point multipliers across that aquifer, pilot point values across that aquifer, and then say, well, here, the pumping test, the pilot point between this bore and the pump was estimated at a T of 40. I'm going to use that estimate as hard data and fix it to that pilot point. And in doing so, we're sort of overvaluing the pumping test estimate. And then it got me thinking, is that actually what we're averaging when we estimate TNS, the average T around that test? It's probably not the case. So hydrogeologists have known that there is this, and researchers have known that there's this weird spatial averaging function when we interpret pumping tests through analytical solutions. And so Butler theorized it as this kind of radiating sensitivity donut that spreads across the aquifer when you turn the pump on. And Oliver and Knight, many others, have attempted to make maps of that sensitivity, because they change with different times, but they show these sort of low bait concentrated values around either side of the pumping test. But they kind of they didn't really close the chapter, didn't sort of explain the full meaning, like exactly the area where we spatially average when we interpret these analytical solutions. And so what we did is hijack the work of the past. So Knight and Klutenberg found a very efficient way to create these maps of sensitivity, because they change with time, and it has to be done very efficiently. So we use convolution to work out these points of sensitivity across the aquifer, and then we use simple inversion theory to create a map of real T in the aquifer and S to the estimate, that an interpreted estimate of T and S from pump test analysis. There's a nasty, horrible equation to work out that sensitivity. I won't go into it. But this is where I lost quite a few people in my last talk, and in the paper, you know, I've had experienced high pumping test analyzers kind of just say, like, get hold of me and say, I don't know what you mean. So I thought I'd oh, it's gone. So anyway, I thought I'd just make this slide to explain this R dash. So the R dash is the spatial averaging function. So what I'm saying here is that the estimate from pump test interpretation, T and S, is equal to the spatial averaging function multiplied by real T and S. And on this frame here, this is the spatial averaging function at one moment of time, at the very start of the test. And in linear algebra, when we multiply these matrices together, we got to go row by column, like row times column plus row times column plus row times column, and it's an integration. So what I'm showing here is that multiplication operation. I'm going through the rows and the columns, like all the rows, these yellow, each frame is just one step of the integration until I get to 100% of the aquifer. And so that's what I'm showing here is that. So this frame here shows the real aquifer. So it's just, we know this is a synthetic aquifer, obviously, but we know that the mean T is 100 meters squared a day. It has some geostatistical model to build it. But what I'm trying to show here is that if high values of T exist within these values of high spatial averaging, notice how on here on the right, you can see that accumulating integration of T go up and down. So you can see where those yellow squares are over where there's low spatial averaging, nothing happens, nothing really gets integrated. But then as I pass through the red and the blue, it jumps up, it goes up, and it goes down. So it just depends. If that coincides with a high zone of K, a high zone of T, it'll significantly change your estimate of T. That's kind of what I want to show there. But it's not that simple, because T is dependent on S. So we actually have to, the multiplication is two, the spatial averaging function is two rows, and real T and S is two columns. So what we end up with is not just one spatial averaging function. We have four spatial averaging functions. We have the averaging of real T to the estimated T from TICE. We have real S, which I'm showing at the bottom here, to the estimate of TICE interpreted S. So it's sort of this value here down there. But they also cross-influence each other. So real S can change the interpretation of T, and real T can change the interpretation of S. And that's kind of what the first paper wanted to show, is in detail those maps, because these change with every minute of the pump test. So that's kind of what I wanted to show in that first paper. we show that spatial averaging function. Same thing at early times. If there was a high zone of T, like there was a real fault or something there, and you interpreted that first 86 seconds of the test, that fault would significantly change the estimate of T if it was within these bright colours. And what happens is, as that sensitivity donut spreads across the aquifer, the averaging process dilutes. So you can see here, after 1 day, you're essentially averaging. You won't see anything close to the wells. It just becomes an average over a very large area. And in this case, I see there's a little bit of colour to it, because I'm actually equally weighting all those very early estimates. But this is very uncommon. You know, most of the time we use Cooper-Jacob, and we're basically just interpreting this massive spatial average. So this is what I'm showing here, is that if we perform Cooper-Jacob interpretation, this is T to T. You see there's no very low spatial averaging. And you just see when we do that matrix multiplication, that integration, it's just a linear, you know, we just accumulate, multiply and integrate, and we reach the exact value of 100 meters squared a day. So hopefully that's kind of making sense. So that was the estimate of S to S. So this is a little bit different. It shows that averaging function does dilute over time, but if you have anomalies in S close to the well, that's going to change that integration, the final integrated value of S. And this is probably the most interesting frame here, is this is the estimate of real T. So this is a spatial averaging function of real T to S. So what I'm saying here is that if there are anomalies of T close to the pumping well, so this is a pumping well, this is a monitoring well, it can look like different S. So it can significantly change the estimate of S. And that influence is strong, very strong, and it doesn't dilute with time. So it kind of highlights the uncertainty of S when you use Tice interpretation, if there is heterogeneity in the system. So I kind of my conclusion is that S is just crap, I think, from Tice interpretation. So this is the opposite. This is how real anomalies of S can change the estimate of T. And so it's more, if you look at incorporate early data, it can contaminate it, but it doesn't really change things too much at late times. So I hope that makes a bit more sense now. So just in summary, to try to ram it home, TNS, interpreted TNS is different, meaning it's at different times. The estimate is certainly not the average T between the pump and the well. It's an average of a very large area. And this animation shows that area that you average over. You can just see, yeah, you're certainly not looking at local TNS when you interpret. And the problem of that cross parameter influence. So when there's heterogeneity, I don't think it works too well. So one thing that's not in that paper, I extended those nasty fresh egg sensitivity maps to incorporate multiple wells and the recovery. So it turns out with Tice interpretation, if you're going to do it, use drawdown, but also use recovery, because there's an equal amount of information to be had by fitting recovery information. So that's what I'm showing here. This is just the influence of T to S. So, nasty equation, even nastier equation, which I had to figure out, which was a nightmare. But so I guess, so no, with knowing what we know, when there's heterogeneity, analytical solutions don't work too well. Because the groundwater model needs, we want the spatial estimate of T and S. So we want the likelihood, so the mean T and the mean S, usually at these big regional cells around the pumping test. And now the pumping test, like real aquifers, operate at a very fine scale. And these pumping tests often operate at a very fine scale. So we need a fine scale numerical simulator to interpret these properly. And the other thing is, we don't just want mean T, we want the uncertainty of mean T and S. And you can't really get that through pumping test interpretation. We want this posterior standard deviation of T and S to inform our regional model cells. So how do you do it? So what we should do is through a fine scale numerical model like ModFlow 6, we make, like in this case, I have 1 by 1 meter cells. I want to represent heterogeneity of the aquifer in these ModFlow models. So I use some sort of geostatistical simulator like FieldGen or SGens or whatever to create that assumed heterogeneity. Sometimes it's a bit hard to know what this geostatistical variogram looks like, but this is what we came up with. It has a lot of variability. You make 500 versions of this, and then you just run those models and store drawdown at each of these monitoring wells. So we do that. But the problem is that how do we get regional TNS from those fine scale models? They don't have parameters. They have sort of realizations from FieldGen or something. There's no adjustable parameters here. So how can we efficiently assimilate pumping test data? Well, what we can do is we can operate ModFlow model at these fine cells, run the pump test, and we can upscale, because that's what we want to do. We want to upscale to these, in this case, 10 by 10, 100 by 100, 200 by 200 meter regional model cells. And that upscaled value becomes our prediction. And we can do this really efficiently with this new thing, this magic software that John sort of released with the data space inversion. And so data space inversion is typically used to calculate a prediction. So you might run 500 versions of a model, and you might say, what is the drawdown at this point? And what is the uncertainty of drawdown at this point? Well, that's what I'm doing here, is that I'm actually, my predictions are my upscaled parameters, my upscaled T around the pumping test. So at every point of the aquifer, I can calculate the likely T and the uncertainty of T. And it does this with magic. It does it by creating a covariance matrix of the observations. So on this axis, like drawdown observations from those 500 models versus my predictions, which is upscaled TNS at every regional cell. And then we decompose that covariance matrix and we build a statistical model. And that model, I'll call it the DSI model, that model can be used just like a real model. Like we can use PEST and calibrate it as if it was a model with adjustable parameters. And it runs in about 0.01 seconds. So you can do wonders with it. So just to make this clear, because I know I've gone pretty quick, the first steps is new methodology is we make 500 versions of the aquifer in a fine scale model. We run that. As we run them, we upscale and we store the mean, the geometric mean TNS at every cell. We use DSI to calibrate that model, and it takes about 30 seconds or something to calibrate it. You can calibrate that model with IS or SHP. You condition those realizations of these upscale parameters to the real pumping test data. So you fit the pumping test data just like you normally would. So just an example here. This is in that second paper. This is a synthetic example, but we say this is a greenfield site. We eventually want to make a regional model that is going to predict drawdown from an open cut and maybe the movement of contaminants. What we're going to do, so years ago, a hydrogeologist ran a 9-hour pumping test. The drawdown data was lost. So someone used Cooper Jacob. No, they used TICE and they fit TNS. We found a report, there's a table. Can we make use, and that's the only opportunity we have to get more data. Can we make use of this data to reduce the uncertainty of TNS? In this model, we need to make a prediction. So what the paper describes is let's pretend we don't have these real measurements of drawdown. Let's pretend we just got these TICE estimated T's and S. We can synthesize those drawdowns as these red points. And then we can pretend that those red points are our conditioning data for a PEST DSI exercise. And it works pretty well, better than nothing, I guess. You run 500 models, convert it to a DSI model, and then calibrate that model. But in this example here, what I'm going to show you today, we're going to pretend that we found the data. We use every scrap of that data because there's good data at that early time that we miss if we sort of just use Cooper Jacob. And here's the result. So yeah, again, I just run 500 models at the fine scale. That is reality of T. That is reality of S. This is upscaled reality of TNS at my regional cells. And look what DSI has done. Like it takes seconds, but I'm able to resolve pretty well the mean T around the test site and the mean S around the test site. And those estimates of S are actually meaningful. They're not, junk from TICE interpretation. And not only do I have that, I have 500 versions of this at each cell. So I can show you the posterior standard deviation of TNS at any point of that aquifer. And as you can see, it does a pretty good job of replicating reality. And so in the paper, I describe the worth of additional measurements. And then because I have the uncertainty, I can calculate the reduction of the uncertainty. So basically the stronger the green, kind of purple color, the more I have reduced uncertainty from the pumping test. And rather obviously, if I use all data, drawdown, recovery, and even flow recorded at in that pumping test, I can reduce the uncertainty of TNS by up to 80%. And that, like depending on your prediction, that could be pretty significant. So like I've done a lot with this historic pumping test, and that's kind of what I wanted to show. It's certainly better than just a fit, a number in a table from Tyson interpretation. And so the question is, with these new ensemble methods, why don't you just use IES to fit this data, these really efficient ensemble methods? Why don't I just make 500 versions of this aquifer? What I would have to do, and then calibrate it, but problematically, I'd have to parameterize each one of these model cells. I need to operate at that fine scale. So I did this. So I ran IES with 2 million parameters. And I set the pump test data, and it took days. That was on my supercomputer of like 120 cores. So it's not really like practical at all. But problematically, it didn't actually fit the data as good as DSI. Like DSI took like a couple of minutes on one PC, but you can see it's done a fairly reasonable job. But what I'm getting at is that with my methodology, I am operating at this fine scale. So it's not, like we do get these upscale parameters, but we actually undertake the pumping test at the fine scale. So I thought, well, these realizations don't have parameters. We can paint these fields of transmissivity with whatever we want. Like they can have channels through them or whatever. Like this is just from field gen. But we thought, wouldn't it be nice if we can identify these linear features like faults from a pumping test? Because that kind of, from what my experience is, like we did this, we tried to find faults at the OB31 side, and it was kind of unsuccessful. The Tyson interpretation just could not deal with it at all. It was too heterogeneous. But I thought, when I make these 500 realizations, I'll also scatter the array, I'll paint the array with these random faults. I know nothing about these faults. I just know that they're orientated north, south, and east, west. I don't know if they're conductors. I don't know if they're resistors. I'll just randomly generate them in those 500 models and then use DSI and see if we can see the location of these faults. But it turns out what we can do, what DSI really needs to see a strong signal. So what we came up with was, rather than just making the geometric mean, so this is the regional cell, rather than just making a geometric mean of all of these fine cells to identify this fault, what would be better is if we harmonically average, like directionally average T. So what we do is we go row by row and harmonically average T. And if a resistor is there in my realizations, it will show up like a sore thumb, like the estimate of the estimate of that upscale parameter would be very low. So it just sort of amplifies the signal of the faults. And then conversely with conductance, if we want to make these faults really stick out, I arithmetically average T over this regional cell, just to boost the signal of the faults. And so, yeah, this is just the results from another DSI run. So what I'm showing here, the blue lines are the real faults from my synthetic reality. And the green cells the likelihood of there being a fault in that regional cell. So the stronger the green, the more likely there is a real fault. And, you know, I mean, there is a little bit of noise here, but it's done a fairly good job. It resolves faults. See, it's resolved these X-orientated faults particularly well when it exists between faults. And then you can see here, I mean, sometimes it hasn't got the exact location of the fault right, but you can see there is some resistor here. So I don't know. I think it was actually fairly successful given what we're doing with only 500 realizations and DSI. But anyway, I kind of think it's cheating a little bit because I know the orientation of the faults. I know there are some here and some here in this direction. What if we don't know anything about the site? We don't know if there's faults there at all. And we don't know the location, like the orientation of those faults. We don't know if they're resistors, conduits. Like this is the, oops. Oh no. Power.
What?
It's a whiteboard.
Interpretive dance, mate.
No, the I'll have to repeat it. But yeah, basically the idea is you don't know anything about the orientation of the faults. Can we find an efficient way to do like a range finding exercise to find the most likely orientation of multiple fault orientations and at the same time fit TNS? So yeah, the next slides so would show that. I think we thought that this HDMI cable was a power cable.
Yeah. I think Kelly's gonna bring one in. Oh, that sucks.
Oh my God.
Why to build the suspense?
Maybe are there questions on the earlier stuff? That's still like, because that's bloody hard, you know, like it took me, you know, months to get my head around all of this stuff. And I was like doing it as a PhD student. Is there any kind of anything that any questions I can field? Things that are still not clear?
Neil, did you do any experimentation to see if having additional points of drawdown data, like with an extra pumping test, whether it actually helps with your uncertainty reduction, just using that DSI method?
Yeah, like some of the experiments, I had two.
Yeah.
I would sort of do a pump test and then wait for that to recover, and then sometimes have like before it's recovered, like induce more drawdown. And it did, yeah. I didn't like specifically target that, but yeah, it would make sense. We know that drawdown, the propagation of drawdown is going to have more sensitivity. That sensitivity donut's going to radiate out, and if you've got bores to see it, it's going to reduce uncertainty.
Maybe a quick one for you, Neil. So I'm guessing this is all in a single layer world where you've got your, nice thick continuous aquifer. We looked at what happens when you have anisotropy and
Well, I didn't get to it. So it was planned because I kind of had some of these, it was a bit ambitious, but I said, can I like make like a flume model of an alluvial system with like 100 layers and then run 500 versions of that aquifer system with a pump test and then do the same upscaling. So I'd like to say, well, actually, let's reduce this to 2 layers with these big cells. We'll just geometrically average it. But like, we were kind of thinking, maybe that's just like too much for DSI to, maybe it's just too much. Don't know. Someone else should do that for their PhD. Are we back?
Yeah.
Yeah, cool. So anyway, and then, hang on, for some reason.
We've got to go 1.
I'll pick
1.
maybe.
Not that one.
Yeah, it won't go down. Oh, cool. Yeah. So the initial thought was, can we just rotate? How about we just rotate the mod flow grid? But that became problematic. We'd have to run 500 versions of the model, rotate the grid, or maybe rotate the bores, and then calibrate that model, and then rotate again, calibrate that model. It could take friggin' ages because I want to estimate, like 40 degrees of possible fault orientations. And then I was in the shower one day and I just thought, why are we friggin' rotating the grid? Why don't we just rotate the boards? It kind of just, it was a bit of like a light bulb moment. And so what I do is I have one orientation of faults, and then I create these phantom monitoring bores at 5 degree orders of rotation. I run mod flow and I store drawdown at that, like at -5, at -10. And the idea is, like, what we're doing effectively is actually rotating the faults. And so that this would be one set of training data that you would feed DSI. And then the purple set would be the next set of training data that I would feed DSI. And you batch all this up and it takes seconds. But it's just an incredibly efficient range finding exercise. So essentially what I have is I end up with 40 DSI models that take 0.1 seconds to run, and then 40 PES files. And I just use IES or just PEST HP to calibrate each one of those 40 models. It just takes a few minutes. But what I get out of those, so here's the results from those 40 degrees of rotation. I can actually look at the DSI model's parameters. So DSI will give you these random statistical parameters. And if you sum the square of those parameters, it's also known as the sum of chi squares. And if you look at those, plot them, and you basically find the minimum of those sum of chi squares, and it points to the most likely orientation of the faults. And it did a pretty good job. So we can take that range and then have a look at the likelihood of there being, like those maps I had before, the likelihood of there being a fault. If I overlay the likelihood of there being a fault with the real orientation of the fault, it's a little bit messy again, but look, it's done a pretty good job of resolving this fault here close to these wells and a fault, a resistive fault somewhere down here. You can do this with IES. You can do this with post DSI HUNC, and they pretty much produce the same result. So finally, let's just apply this to a real world example. This is OB31. I just keep it simple and I'm just looking at one pumping test. And again, like this pumping test was attempted to be interpreted with TICE, didn't work. But I do this range finding exercise. So run 500 versions of the model, store drawdown at every orientation. So you see these animations here, see the degrees. So you can sort of see this is the prior range of drawdown. You can see it as we get further away from where the real, I don't know where the real faults are, but as we get further away, we see the fits get worse. So let's run DSI, do that rotation thing, and look what we see these. I mean, it's not quite as clean as that synthetic example, but it shows that there's probably a fault orientation here. So if I just look at the I can isolate them by just looking at the conductors. I see there's a local minimum here, a local minima here. If I look at the phi values from those pest models, so phi is the sum of the squared residuals, modeled minus real drawdown, I can again see these local minima. And then at the end of the calibration, I can look at the posterior data conflict. So that's basically, I'm working with an ensemble here. If all of my drawdown in the calibrated model does not cover the real drawdown data, I'll log that as a posterior data conflict. I count that, and I can see that there's a minimum here, that this is probably where there is a fault, like a fault orientation. And then finally, we do that range finding exercise. We identify, like what I said, is there are two sets of conductive faults. There are two sets of resistive aquitards. Let's generate 500 versions of these fault orientations. We kind of just polished that range finding exercise. We're not doing that rotation thing anymore. Let's run DSI, do all that upscaling stuff. This might give us a clearer picture. And it does, I mean, I haven't got too much detail here, but it has identified the correct orientation of faults. So they guess that the faults are at these orientations. We've kind of resolved them in their locations. But not only that, we've got T and S of the entire aquifer as well, and the uncertainty of it. So I think that's it. So I might have gone a bit over time, but what I want you to take home is that TICE interpretation, when there's a lot of heterogeneity, it doesn't work too well. And when it does work well, you're only averaging the bulk transmissivity. S is crap. Local heterogeneity can only be confidently identified through like stochastic representation of heterogeneity with these real numerical models. And I've shown you a way that you can do it really efficiently. And you can extend that method to faults. That's it.
Thanks a lot, Neil. Do we have any questions online or in the room? Let's go first online, I guess, if we have any questions online. We have one. It was made halfway through the talk, I think. How does the real T compare to the T estimated from the recovery phase of the aquifer test? Did you get to?
Yeah, it's kind of the same. You know, like in my case, I have a mod flow model, so Q was constant. So as I induce drawdown, you get that spatial sensitivity propagating out. But when you just look at the recovery information, it's almost, you get that spatial, that sensitivity donut just sort of goes backwards. So it's basically somewhat identical to drawdown and contains just as much information.
Excellent. Any more questions online?
Yes.
From James. How does this work influence how you design a pumping test?
Well, I guess now, like from those maps of spatial sensitivity, you kind of see where like you're going to pick up structure. And if you must use pumping test interpretation, analytical interpretation, I've kind of said, well, when I interpret it, I'm going to average the lobes, the outside of the pumping test. That's actually what I'm looking at. And actually for a model I peer reviewed, that was, the thing is like, I want to know T between this pump and this pump. And they thought they were going to get it, and they were just going to use TICE, but it was like, no, you're actually averaging the outside and the outside area of the test. But I guess, if you use these methodologies and actually like a numerical simulator, you can resolve things between wells. But I guess it's kind of looking at like my ability to resolve faults. I got better results when it was between the wells. So I guess kind of obvious, just the more pumps, the better. The more wells and pumps, the better, really. Yeah.
I have a question in line with that. Did you experiment? Sometimes you have only one monitoring well, or maybe two. If you're lucky, you have 4 or more. Did you experiment how accurate the maps of predictions look like with different amounts of monitoring wells?
I did in that in the fault analysis. That's where because I did live in this world where there's one pumping test and 3 bores positioned right beside it. And I did get a bit hung up on that, but yeah, as I was doing this fault analysis, yeah, you do notice that you do reduce uncertainty of, when there's more bores. I didn't get into I didn't thoroughly examine it, but it would make sense, with more bores, the more uncertainty is reduced.
Yeah.
Sorry, mate, got another one for you. Just that thing with the sum of the chi-squared, that's actually pretty cool because you're actually able to see something there that you can't see in the objective function. So when you calibrate your ensemble, like you had 2 little local minima there, you didn't have in the other one. Why do you think that is? Like, how do the principal components bear more information about the fit of the model than the objective function?
It's a good question. And
Super cool.
and it's actually part of what I have to write about. So I think I don't know. and I need to find out. But, yeah.
It's cool. I mean, no one would think to look at those things, I guess.
Yeah. Yeah. Oh, yeah. So Tariq.
JJ.
Oh, sorry.
Yeah, I have a pretty simple question. Like, so when you upscale your model from a fan model to cost model, do you select the cell size, or does the cell size of the cost model impact the result?
I didn't look at that. I suppose the uncertainty is only going to increase. Like it's the geometric average becomes a bit more important then. You're averaging over many more cells, and fine scale structure becomes a bit more diluted. And but yeah, I didn't specifically.
Yeah, because well, maybe many years ago, I've seen some papers talking about the upscaling techniques, and they're always talking about the existence of the REV, like the representative element volume, or So I'm not sure, like it is something related to your topic, when you do the upscale.
I think for another PhD student.
Yeah.
Yeah. Yes.
Eli, I have one last question, and it may, it's so basic that it may sound offensive, but I guess it's for the for the everyday hydrogeologist who's working on a site and needs to get work completed and has a supervisor looking after them and checking, hey, how are you going? When is this gonna get done? How, if someone says, hey, I'd like to try this methodology, it's really nice and can give us more accurate estimates. And the cost and the effort versus reduction in how can we justify to a supervisor who's like saying the investment or the effort, what's the effort versus reducing, I don't know, how many orders of magnitude in the uncertainty of the result? Is it, do you think it's something that will become super popular soon or only in special cases?
Well, it could be, because Jeremy, from Best Plus Plus, he has that field conditioner. And that's kind of designed to take estimates of pumping tests and say that the most likely measure of T at this point in the aquifer is this. And then it generates realizations with kind of that as like, I'm not sure if it's soft data or hard data, but like what I can provide from this is not only that the most likely version of value of T, but the uncertainty of T. And we've shown that it can reduce uncertainty by 80%, 20% or something. And so, and I guess if you don't have good data, that could be really significant. Maybe the model calibration exercise wouldn't reveal that because you can't really run that pump test in your regional model. But the goal is to automate this, put it into a Python package so that it is like click, 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 and like an afternoon's work. Because, like if you just use FlowPy and you say, where's your pump? Where's the pump located? Where's the wells? Where's your drawdown? Here's a CSV. It could do all this automatically and use these Python libraries to generate realizations and do all that BSI stuff all in the background. And that's something for another PhD student to do. And then, you could use like Damien's GPU solver or something, just, like you're just doing it on your computer. Like get these big detailed models to run super fast and then use DSI to fit it. And it's an afternoon's work. So at the moment, yeah, it's a bit hard and a bit out of reach, but maybe someone could automate it. Yeah.
It would be a dream to have that work well to them.
Yeah.
Anyone else? Yep.
Yeah, so, thanks, Neil. I guess what you've shown highlights the importance of understanding scale of both things from models as well as our field observations. And unfortunately, a lot of the time, you can have sparse bore coverage and large gaps in between. And from what I can understand from your method, you're getting an idea at a certain distance around where we've had these bores, but there could still be quite a big gap before you get to your next bore that could have been pumping test at. Is there a potential, like, we're going to be too reliant at really small areas when we're trying to understand something that might be so much bigger?
Well, that's it. Like, I guess we don't often even know the area of the aquifer that we were assessing from a pumping test. And we've seen that it's actually kind of localized. We're just reducing the uncertainty. If we use this, we're reducing uncertainty just around it. So
it just shows you that more data is required, more long-term data. Like this was just a 9-hour test.
Mhm.
But so imagine if you did a longer test, that sensitivity donut propagates further. You've got more bores, you'll reduce uncertainty a bit more, but you do see concentrated reductions of uncertainty close to the well. Part of that was though if we had measurements at the well.
Yeah.
But yeah, it just highlights that we still won't know much about the aquifer. There'll still be heaps of uncertainty.
So it kind of feels like you might be finding a way to reduce uncertainty for just a small patch, but
Yeah.
in the overall scheme of things, how meaningful is it to deal with this little patch out of the whole thing?
I know it's squeezing every bit of data out of these pumping tests. And I guess it's more data than has been used in the past, essentially not used.
Yeah.
All right, sorry, I noticed there's one more question, but it's kind of late. May I suggest that anyone who's got more questions, just get in touch with Neil directly. I'm sure he can tell you all about it. And thanks everyone for coming. Yeah, it was pretty nice. Thanks, Neil, especially.
Is any